screen share. So questions. Final call for homework 8. Um, Last chance. So I take it this means everybody is done with homework 8? All right, go for it. You can use your microphone if you want. All right, I have output for standard error in my script to do some troubleshooting. Can I leave that or should I clean it up? Yeah, definitely clean that up, because to grade these things, I'm basically going to run your script against those 5 input files, and I'm going to compare the outputs using the difference command. And if they're different, you're going to lose, points for that right off the top. And then I'll dig in and see if those differences are, major or minor. But you really want to mimic the output exactly from the temp files if you want to get full points. So definitely remove any debugging output, but my suggestion is just comment it out in your script, right? Leave it inside the code, just throw a number sign in front of those debug lines so that your output is nice and clean. Does that make sense? Cool. All right, other questions? All right, well, this is where Section B is going to actually get ahead of Section A. For some reason, the second class tends to run about, it feels like sometimes 10 or 20 minutes behind the morning class. And so there's a slight phase shift in coverage of topics. But this morning we spent about 40 minutes in the Section A class going over questions related to Homework 8. So we'll actually pull a little bit ahead material-wise here. It all ends up synchronized at the end. All right, well, let's go ahead and talk about processes then. So let me bring up a window here. All right, so we talked a little bit about processes yesterday and about the idea that every program, every bash shell, every login session is its own process, and we looked at some PS commands that we can use to see processes that are running either on the whole system or associated with our terminal session. And so let me write some test code. All right, so here's some code which is just going to hang out in an infinite loop. It's going to say hello every 2 seconds. And I'll make this executable and I'll run it, and it does what we'd expect every 2 seconds. Prints out a message. And if I want to interrupt that, what do? I hit Control C. So I hold down Control, I press a C, and the program terminates. All right, that's the usual way to end a program. Now, if this is running and instead I hit a Control Z, right, it does something similar. It brings me back to where I have control over my bash session. I can type commands, right, and I can run my program again. And that's still not working, so I can Control Z and I can, VI main, and I wanted to, let's say, do an uppercase hello, so I can run that, and that seems to work, right? The thing is, Control Z does not terminate a process. And if I do a PS right now, I have 3 versions of main all sitting out there still alive. They're not running in the sense that they're suspended. Control Z is a suspend request. But they're still out there, they're taking up resources, they're cutting into my quota of how many processes I can have, and it may be that at this point, if I had to assess a program and I said assess, I'd get an error message saying no process slots available. Right? If I do this when I'm editing, if I Control Z out of my VI session, then I get those annoying swap messages when I go back in and so on. So Control Z has a use, but it's not the way that we kill a program. Okay, if you're running a program and you want to terminate it, Control C, that kills it, and now, I have 1 fewer of my mains. But sometimes we do a Control Z because we want to temporarily suspend a program, right? So if I use the command jobs, I can see whatever programs I had running that I've suspended. And I have 3 options at this point. I can kill the job, right? Or I can bring it back into the foreground, so I can say let's foreground job 1, right, so that's continuing to run. Or I have the third option of saying go ahead and run in the background. So I can say background %1, and now that job's continuing to execute, but I still have control over my bash session. So it's running in the background simultaneously with other stuff. So now I have 1 version of main running. I have another one that's still paused. I could start that second one running again by throwing that in the background. And now I've got 2 of these things running simultaneously. And I still have access to my shell. And this can be, unfortunate if you're in the middle of an editing session, because you get weird things like this. And if you're in VI and you're in command mode, you can hit Control L to refresh your display. But if you've got stuff running in the background that's sending information out to standard out, that's going to disturb the display that you're seeing. Now, this is not changing my file, right? And even if I'm in insert mode, this is not changing my file. This is just stray stuff that's being sent to my display. Just like if somebody comes along and sends you a message, right, you'll see it looks like it's in the middle of your file, but Control L will refresh. Alright, so I've got these 2 jobs running. I want to make one of them go away. One way to do that, I can use the jobs command and see my jobs. Let's say I want to kill job 1. I can just say kill %1. All right, and the next time that I hit enter, it'll tell me, that job 1, which was main, has been terminated. Job 2 is still running out there. So I can kill it by saying kill %2. I could bring it to the foreground and hit Control C. Either of those would kill it. Let me just bring it to the foreground, Control C. And now that job is gone. And if I do my PS, right, there's nothing there except my bash and my PS command that I just typed. So the percent, I've only seen that used for interacting with jobs. So let me run some stuff in the background here. So here's my main script running in the background. So I can say background %1. I can say foreground %1, and so on. But I don't know if it has meaning in general. I've only used it with job-related commands. All right, if I do a PS, I have another way that I can kill this. If I know its process ID, which is 12938, right? That's the main command. I can say kill 12938, and that'll terminate it. So if this is a job that we started and either put in the background with an ampersand or Control Z and then did a background command or not, right? We can use this % symbol to get a hold of it. But if, for example, I have, you know, a different session, on this bash session, I have no jobs, right? So there is no, you know, %1 job to kill. But if I search for, well, that's a lot of jobs. If I search for, you know, a process that's running main, I can see there's a process with ID 13004, which is this thing that's spitting out hello over here. So from here I could say kill 13004, and over here that job's been terminated now. So the kill command we can use from bash, and it basically says send a message to a process. In this case, I said send a message to this process, which was, you know, running in a different bash session. But any process that's owned by me, by Nick, right, I can send a message to with this kill command. And you can send different messages. So if you do kill-L, you'll see the numbers for these different messages. So I don't know what's going to happen if I send a sig FPE. But let's try that. Sig FPE is signal 8. So let's do a kill-8 on 13449. Well, my program over here terminated, and the reason it gave me was it got a floating point exception. Right? Well, there's nothing in main that does any floating point, right? It doesn't do any arithmetic at all except comparing 1 to 1. But it doesn't know that, right? All it knows is it got a message which said floating point exception, right? He got that message because over here I sent a signal, signal number 8, which is designated as a signal you send when some process does something it shouldn't do with floating point numbers, like dividing by 0. So even though this doesn't do any floating point, right, the process is set up so that if it gets a sig FPE signal, it will print out a message, right, and then terminate. So these signals are just ways of passing information to a process from another process. And it's not as nuanced as, you know, being able to send a detailed message, but it's a poke, right? And you can poke a process, you know, in the arm, you can poke it in the leg, you can poke it in the head, you can poke it really hard in the head, right? So if you kill something with a 9, that's knocking the process really hard in the head, and that will terminate the process. If you hit a Control C, that's doing a SIGINT. If you just say kill, that's doing a sig term. If you say kill -24, that's doing a sig x CPU, whatever that might be. Let me try one more thing. Let's see what sig stop does. So kill 19, 13, 591. And my main process is stopped now. It's acting the same way as if I had hit Control Z from my keyboard. And if I look at jobs, I can see my job there and it's stopped, and I can background it if I want. And I could foreground it and so on and so forth. And it's still sitting out here running. Right, I can still see it, and I could kill it with something else. Let's send a segmentation violation. So I'll send a signal 11, that's seg v. And so what do I have over here? I got a segmentation fault. We don't normally get seg faults from bash, but there's not really a seg fault that took place, but I pretended there was. I sent a signal to this process saying, hey, you just got a seg fault. Now normally that comes from the memory management subsystem. You try to access location 0 because you forgot to initialize a pointer, and you're trying to take the string length of a string that hasn't been initialized or something, and the memory system says, hey, there's a problem there, there's a segmentation violation. What does it do? It sends a signal 11 to the process, and your program says segmentation fault, and it exits. All right, so this is the way that processes one way that processes communicate with each other. And it used to be that, you know, when you got this fault and it said core dump, you would have a file in your directory called core, and that would be a copy of the memory of the system. This was when, you know, systems had like 64K or 16K of main memory. And so there'd be a file showing you all of the contents of memory, and then you could go in with a debugger and try to figure out what caused the problem. Yeah. Cool. Yeah, someone just asked if it made a core file. All right. So you might hear people talk about dumping their core on you sometimes. That's usually a throwback to something like this, when you've had a really bad day and you just need to like get a bunch of stuff off your chest before you can go on with your usual business. Sometimes you say you're just core dumping, you know, and it's just putting everything out there for future reference or whatever, and then you can go on and have dinner or whatever. Anyway, all right, so signaling, right? So we can use the kill command and we can send a signal. And again, some of these can be intercepted and treated in a different way. For example, you might not want your program to terminate if it does a divide by 0. You might want it to do something like, say, you know, you entered an illegal number, please try again. So there's a command we can use called trap. And trap works like this. We can say trap and then say what we want to have happen when a certain type of signal is received. So in this case, let's trap this this sig FPE, signal 8. And when we get a FPE, we're going to say echo division by 0 question mark. and we'll trap that. So now when we send a signal, SIG-FPE, to this process, instead of just exiting and saying floating point exception, it should execute this echo statement and then just continue happily along its way. So let me go ahead and run this. So it's doing the same thing, sleeps 2 seconds, says hello. That's process 14104. We'll kill it with an 8. Let me pull this into a separate window for maximal dramatic effect. Right, so we'll kill this process. And you can see my script said division by 0, but it continues running. And we can do that as many times as we want. Now I killed it multiple times while it was sleeping, and then when it came out of the sleep, it noticed the signal and printed out its echo message. But these don't get buffered up, right? It came out and it knew it had been signaled. So a signal is like a flag, right? You raise a flag. Well, if you raise that flag 20 times, you don't suddenly have 20 flags. You have a flag, you know. And so it responds to that. Some signals cannot be caught, though. In particular, signal 9 cannot be trapped. If you send a signal 9, it kills the process right away. And so if you have a job that's stuck in some kind of loop and you can't get it to stop, you can always kill it with a kill-9. And I think it will warn you about that. Nope, it just happily tries to set up that trap, but it won't actually trap it. Right, it's untrappable. Any way to turn itself into a background job? That would be interesting. So $$ will give us our own process ID, right? So 13007. So let's try this. So what was our signal for stopping? I'm sure we can suspend ourselves. I don't know if we can get ourselves into the background, but we can send a sig stop. That's a 19. Let's stop ourselves. All right. So we can have the job stop itself, but then to get it to continue running in the background, I'm not sure if there's an easy way to do that. That's an interesting question. We can also, you know, kill ourselves. But that's not terribly useful. But if you don't want to do an exit, I guess you could do that. Now a kill-9 is pretty brutal. Okay, when a process dies, it usually doesn't just stop right there. There's a bunch of things that happen to clean up resources that have been consumed and so on and so forth. A kill-9 potentially circumvents some of that. So you really use it in kind of a dire emergency situation. But you can use that to terminate a process. So what we can do is capture SIG_int. And SIG_int is generated when you hit a Control-C. When you hold down Control and press C, it doesn't just magically kill your process. What it does is it sends a signal to your current foreground process, and that signal is a SIG_int. Well, if we trap SIG_int, then when I hit Control-C, it just says, haha, but the process continues running. And so Control C will not terminate this process anymore. Now I can Control Z it, and I can kill it like this. But I can drop that sig stop signal also. So I can't Control C it. Oh, but I can still Control Z it. So I don't know if that sig stop can be trapped. But it at least can't be trapped like this. Let's see, I read something about set-m. I don't know what set-m does. But if you look at bash, this is a hard thing to find because set's such a common word, but there's a whole bunch of things that you can set that control things like, you know, will Control D exit bash, or do I have to use the command exit? Or how many times in a row do I have to hit Control D for it to register as an exit from my shell? Or should I overwrite a file if I try to redirect output to it? Or should I warn the user that the file already exists? So there's all these variables that you can set that control the behavior of the bash shell. I don't know what a -m might do. But if you can remember what you read about it, that could be interesting to look at. That's for binding. Yeah, you can change your key binding. Set-M monitor mode. Job control is enabled. The option is on by default for interactive shells on systems that support it. All processes run in a separate process group. When a background job completes, the shell prints a command line containing its exit status. Interesting. So interactive jobs are different from non-interactive jobs in a number of ways. And if you look at your bash RC, you'll likely see some comments in there where things are done differently depending on whether this is run from an interactive shell or from, you know, just an invocation of bash to execute another command. For example, you know, when I run the name of a script, when I say main, this is being run through bin bash, right? But it's not what we consider an interactive interaction with bash, right? And so you may want certain things to happen in bash RC when you run it from a terminal, and other things that don't happen when you use it to execute a script. But I don't know what exactly we would do with a -m, but it affects this idea of printing messages when a job is stopped and so on and so forth, I think. All right, so we can trap signals in here. We can send signals, and there's always default behavior for signals. So here's, you know, our main loop running again. And I'm searching for my process by just looking for a job owned by Nick that ends with the word main. Interesting. Do I still have 2 jobs? I got 2 jobs running. Let's kill both of those. Okay. So let's run this job. And that's job 14608. Alright, so let's kill sig user 1, 14608. Alright, so job terminated, and the message it said was user defined signal 1. If I do sig user 2, $15.60. Right, user defined signal 2. So so a lot of these signals, the default behavior is to terminate the process, and print a message in some cases. But we can customize the behavior of these using this trap command. And so we have the potential to do something like this. Here's process 1, process 2, and this can be doing something, and this can be doing something, and these might be independent processes, but suppose they want to share information. Now, if we create both of these from one process, we can make what's called a pipe, right? That's what happens when you say command, pipe, command. But if these are independent processes, we can still share information, right? And one way to do this would be to make some kind of file, and process 1 can write something into this file, and process 2 can read from that file. And you can exchange information like that. Well, the problem with that is process 2 would need to continually check this file to know if there's a message for it. And it might check this file, well, if P1 is writing a really long message, it might check this file while the message has been partially written and pick that up and think that's the whole message. So what you could do in this case is you could have process 1 write something into this file and then send a signal, right, using a kill to process 2. And process 2 can be set up so that when it receives that signal, it runs a function in itself that will go off and read from that file. And you can do this, bidirectionally if you like. And that's one really rudimentary way that you can set up message passing, information sharing between two scripts. I had to turn my heater up because it's really cold in here. So that's one thing we can do with signals. All right, questions about that? Can you show a very quick example of sharing processes with the signals? Let me wait, and because I want to do this in detail from C, and I think it makes more sense from C. And I think once you've seen it there, then doing it in Bash wouldn't be would be a small variation from there. But I think if I try to do that in Bash right now, I'm going to end up with something that looks pretty confusing. But what I want to do is I want to start talking about processes from C, and we'll get to sharing information through pipes. All right, so let's talk about processes in C. And it's, the same processes, whether we're creating these things from, a command line by typing in the name of a command, or from C by creating a process. But most of Unix is written in C. And so when I say something like, main ampersand, right, or kill %1, those are doing functions that were written in C, right? And Bash is just, this higher level interface we have to these low level system operations for creating processes, manipulating processes, signaling processes. So let's look at how this stuff actually works. And the first thing I want to talk about is something called a fork. All right, so I have to give you a bit of a disclaimer here, okay? Once we start talking about processes, especially from C, it will probably become apparent really quickly that there's really easy ways to take down a Unix system, okay? And there's very little glory in doing so. So, you know, there's some safeguards in place on the Linux server that should keep accidents from happening. But, you know, you can write a one-line C program that will shut down a Linux machine if you don't have these safeguards in place. And forking is the easiest way to do this. So we'll be working with something that makes it really easy to make a fork bomb. All right. If something goes wrong, right, this can happen by mistake. Okay, I've done this plenty of times on my own system. I believe I have process limits in place on the server that should stop this from going badly. But if you want to experiment with this stuff on your own system, make a VirtualBox version of Linux and try to fork bomb it, it's a lot of fun. Okay. But I'm going to ask people to play nicely right on the shared server because I think it's probably not that hard to do a denial of service attack on it because the system is so open, because we're using it for learning and so on. But that's just going to, you know, annoy people and make your friends unhappy. So so with that little bit of a disclaimer, let me talk about fork. So fork is a function we can call from C, and the description is create a child process. Okay, and basically you call fork, it doesn't take any arguments, and it basically returns an integer. It's a PID underscore type, but it's basically an integer. And this is really easy to use. All right, that's all I got to do. And I run that, and it doesn't seem to do anything. Right, I do a PS. I've got, you know, my bash and my PS. I run F1, and I do my PS, and I still got just a bash and a PS. All right, let me make this a little more interesting. Let me put a sleep after here. And let me run F1 in the background. Let me do a PS first. Okay, this is what my process looks like. Let me run F1 in the background, and while it's running, I'll do a PS. And what you see is two processes executing the command F1. Now, I only did F1 once, but I've got two processes. And this first process, process ID 16183, its parent is 2586. That's my bash shell. So this F1 was run when I said F1. This other F1, its parent is 16183. That's this first copy of F1. So what's happened is I said F1, that started running this program, and this program created a new process that was also executing F1. Okay, 20 seconds have passed, so both of those programs have exited. Now, if I don't do this fork, and I just run F1, right, I see my F1 program out there, and it's just hanging out, sleeping. But with this fork, it creates two copies of my program. All right, so what if I call fork twice? I've got 4 copies of my program. And if I kill that main copy, it kills the children processes as well. What if I call fork 4 times? I've got 16 copies of my process running. Alright, it doesn't take very many calls to fork to overwhelm the system. And if I were to simply put that inside a for loop or a while loop, you've got a denial of service attack. Now, I don't have process limits set up on my account on this machine, so if I were to just say, while 1 equals 1 fork, my system would crash, because it would basically run out of resources for creating more processes, and if that happens when the system is trying to create a process, it will likely shut down the system. Now, I put in a 20-second sleep before my process exits, so after 20 seconds this is gone. But what's happening here? I start off with my job F1 and I say fork. When you call fork, you create a clone of your current process. So here's what happened. I executed this statement, this first call to fork. That created a clone of the process. And both of these processes think that they just finished executing this instruction. And so now both of them move on to the next instruction and they both execute a call to fork, which means that this process will create a new child and this process will create a new child. And now I have 4 processes and each of them think they just executed this call to fork. And now all 4 of those processes want to execute this third instruction, which is a fork. So each of those executes a fork. And now I have 8 processes running, and so on. All right, so here's an interesting program. I'm going to call fork a bunch of times, and then I'm going to, system is a way we can run a Unix command from C. So I can say system and put a Unix command inside quotation marks and it'll execute that command. So I'm going to call fork 6 times, which will create 64 copies of this, and then each copy is going to do a PS. And then I'm going to say done forking and I'm going to exit. Don't do this on the server, okay? If a few people do this, it'll probably shut down the server. But let's go ahead and run this. So these jobs are running simultaneously. And some of them, finished forking up here, some of them finished down here, a bunch of them finished here at the end. They're all exited at this point. And so, we've got all these jobs executing this ps-fl command. We've also got some that are listed as defunct. And if you look at the status of those are our zombies. Those are jobs that have finished executing. They should have died, but they haven't gone away yet. And if you were to track the lineage of these as to who owns who, right, you could see how these processes are being created by other processes. But if this job exits while its children are still running, this job can't completely go away. It still has resources consumed, so even though I might kill this, it still has other resources that need to be cleaned up and can't because these jobs are running. This is going to turn into a zombie. All right, so that's a little bit of the weirdness that can happen. What's the less weird part? Let's just look at this fork call. So fork doesn't take any arguments, it returns an integer. So let's just try a simple call. So let's print a message and say we're ready to call fork. And then let's call fork and save the return value in this variable I. And then let's print a message saying we're done with the call to fork and print out the value of I. And I didn't include standard lib, but that's okay. Let's just go ahead and run this. All right. So ready to call the fork. And then it says done with the fork, and I is equal to this value. I've introduced a red herring. That would be an awesome exam question. All right, so ready to call the fork. Okay, that gets printed out once because, you know, that was before we forked a child process. And then we call fork, and now we get 2 of these print messages, right? And we're getting 2 of them because once we execute this call, we've got a parallel process running. And both of them have just come back from a call to fork. They've set I equal to that return value, and they print out this message done with the fork, I equals. But look at the values that got printed out for I. One of them printed an interesting value, one of them printed a 0. And if I run this again, right, one of them printed out 17224, another one printed out 0. If I run it again, one of them printed out 17226, another one printed out 0. So here's the magic of fork. When you call this function, 2 things happen. Number 1, a clone of your current process is created. It's an exact replica. Got the exact same memory contents, the exact same code. The program counter is exactly the same value. It looks like a perfect clone of your process, except the second thing that happens, the return value from fork is different. If you're the parent process, you get back the process ID of your child. If you're the child process, you get back a 0. All right, so that's our starting point. We'll build from there, and we'll see how to deal with processes in more interesting ways tomorrow. All right, have a great afternoon. I will catch you then. Thanks.